Alright, so in the next short while, we're going to see what is the equation that we are actually trying to solve using the finite element analysis. The equation that we're trying to solve using finite element analysis is the differential equation of equilibrium, and you're going to find it in chapter 4. And it's basically, to derive this equation, it's a really simple derivation. If I have an object before deformation, after deformation, this is where the object is, and this is what I'm looking for. I'm looking for this function that takes this object and gives me this new object. Now this new object abides by Newton's equations of equilibrium, because in this configuration, if I take the small object out of this, or small cube out of this material, it will look like this. If this is sigma on 1, again, we assume everything is smooth and differentiable. If things are not smooth and differentiable, I can't write a differential equation. Because of smoothness and I'm able to differentiate those functions, I'm assuming that sigma on 1 is a smooth function all over my object, I can say that at this point I have sigma on 1 plus a little bit more that's related to the partial derivatives of sigma on 1, plus other parts that I will ignore. The equation that I'm interested in right now is the sum of forces in the horizontal direction which is the direction of E1 equal to mass multiplied by the acceleration in the direction 1, or equal to 0 if I'm doing a static analysis. So I'm looking for all the horizontal forces. So the other horizontal forces are sigma 1, 2, actually this is sigma 2, 1. They're equal, but according to my convention, I call this sigma 2, 1 plus how sigma 2, 1 changes with respect to the vertical component multiplied by the vertical component plus a little bit more. I also have another horizontal force, or a few other horizontal forces, which are as follows. This is sigma on 1. This is E1. This is E2. This is E1. This is E2. This is E3. I'm also interested in this force in the back corner, in the back here, which is sigma on the face 3 in the direction 1, and on the front face here, it's equal to sigma 3, 1, plus how sigma 3, 1 changes with respect to this component multiplied by delta x3. Not only this, what other force do I have? If I assume that gravity is pulling this with a gravity force, let's call it G1, or let's call it B1. So this is the Earth, and it's pulling this object in this direction. Yeah.
For that one, should it be x1? Delta x1.
This?
Yeah.
No, because this is in
Yours, well, the horizontal formation.
sigma 3,1 in the back and sigma 3,1 in the front. They are different by this distance.
Oh,
Yeah, is that okay? So the sum of all the horizontal forces that I've drawn has to be equal to 0. So the sum of the horizontal forces are given as follows. You always find that sigma 1 will cancel sigma 1, sigma 2,1 will cancel sigma 2,1, sigma 3,1 will cancel sigma 3,1, and you're always going to be left with those small components. Now these are stresses, so I'm going to multiply by the areas. So you'll find the following. So sum of forces in the horizontal direction is equal to 0, or in the direction of E1 equal to 0. You'll find this partial sigma 1 by partial x1 multiplied by delta x1, delta x2, delta x3, plus partial sigma 2,1 by partial x2 multiplied by delta x1, delta x2, delta x3, plus partial sigma 3,1 by partial x3 multiplied also by delta x1, delta x2, delta x3, plus the force of the gravity, the mass, multiplied by the acceleration, by the gravity acceleration, so mv1, but I'm instead of for mg1, the gravity component in this direction, but instead of mg1, we write it the mass is equal to the density multiplied by dx1 multiplied by the volume, which is dx1, dx2, dx3. And the component, we call it v1. This is the mass, and this is the gravity. And this is equal to the mass, which is the density multiplied by the volume, multiplied by the acceleration in the direction 1. If you divide by the volume, you'll end up with the equation of equilibrium that any person working, whether in mechanical or civil or any mechanical system, should know by heart, which is the sum. So if you can repeat this for E1 and E2 and E3, and you get the famous equation that says partial sigma gi by partial xg, and small. Oh, I'm sorry. All these should be small. Note, replace x with x. Simply because we're working in, apologize for that, we're working in the, this is all in the deformed configuration. So all these equations are functions of the small x. Sorry about that. So where should we write here? For those who are not here, or in the following derivation, x was used, which is the underformed coordinate, but the deformed coordinate should be used instead. Because we're extracting our object from the coordinates x1 and x2. So every time you see capital X, it should be small x. So the famous equation states the following: partial j sigma ji by partial x small xj plus rho vi is equal to rho ai, where I could be 1, 2, or 3. When I is equal to 1, you get this first equation. I equal 2, you get the second equation. I equal 3, you get the third equation. And this summation sign is from j equal 1 to 3. There are many, if you use the summation convention that we talked about last time, you can write it partial sigma ji by partial xj plus rho vi equal rho ai. And these are 3 equations. These are the 3 equations of equilibrium. Sum of forces in the horizontal direction, sum of forces in the vertical direction, and sum of forces in the third directions. Now, we already used sum of moment equals 0 to establish that sigma 1, 2 equal to sigma 2, 1. So I can't use it again. It's not going to give me any new information. And so this equation, where these equations have 6 unknowns, which are sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 2, sigma 2, 3, sigma 3, 3. I only have 3 equations and 6 unknowns. I'm not able to solve these equations unless I put very restrictive assumptions. Not only this, the boundary conditions of the problems are not necessarily given in terms of the stresses. They're given in terms of displacement as well. And because the boundary conditions are given in terms of displacement, I need to replace this equation with another form of this equation that contains the displacement rather than the stresses. And hence, we move to the next chapter, which is the constitutive laws. But before we move to the constitutive laws, I just want to solve 2 problems, or show you 2 problems. How can we solve, or what would you do if you have to solve these equations by hand for simple structures? So for simple structures, we have to make very restrictive assumptions, otherwise I won't be able to solve these equations. And these restrictive assumptions usually mean I have to assume that my stress matrix has only one non-zero component, for example. So I'm only calculating sigma 2, 2. So I make my differential equation in terms of only one variable, and then look at my boundary conditions. If I have enough boundary conditions for that particular variable, I can solve it. So for example, I have an object under certain stress distribution. I can assume that the only non-zero value for the stress is sigma on 1, and I can solve this problem that you have in front of you. But let's say you have an object that's restrained on both directions, and then you apply a gravity field that's pulling it in this direction. Even with the assumption that sigma on 1 is the only variable, I can't solve it without the constitutive law, because the boundary conditions are given that the displacement here is 0 and the displacement here is 0. So I can't solve the differential equation in terms of the stress, because the boundary condition is given in terms of the strain, not in terms of the stress. Sorry, the boundary condition is given in terms of the displacement, not in terms of the stress. So, in the first problem, I have a bounding condition here. I have this object that's hanging. The radius here, it's a circular object. The radius here is equal to 2 units. And the radius here is equal to 1 unit. And there is a force here that's equal to P. And there is a gravity field that's equal to rho G. The shown vertical beam has a very circular cross-sectional area, radius 2 and radius r, and the radius varies linearly. Radius varies linearly. I'm going to call this coordinate inside the object x2. So for this to vary linearly, therefore r is equal to 2 minus x2 over L. And when x2 is 0, you get 2. When x2 is equal to L, you get 1. There is a concentrated load, P is equal to 50 Newton, which means this P equal 50 Newton gives me a boundary condition for the stress. Sigma 2 at this point is equal to 50 divided by pi r squared. I'm just going to write it P over pi. Has a density 20, a gravity field G is equal to 10 meters per second squared. And here's the restrictive assumption. Assume that the only non-zero stress component is sigma 2. Without this restrictive assumption, I won't be able to solve. And find the stress distribution. Find the distribution of the stress component sigma 2 along the length of the beam. So for me to solve this, I'm going to rewrite the differential equation from the beginning. So I'm going to extract the sliver of the material. The area in general is equal to pi r squared, which is pi 2 minus x2 over L squared. And I'm also going to assume small deformations. What does assuming small deformations mean? It means partial sigma ij by partial small x I is equal to partial sigma ij by partial capital Xi. So small deformations, doesn't really matter which coordinate I'm using. It matters for large deformation. I'm going to extract a small sliver of the material and say, if this is sigma 2, this is sigma 2 plus a little bit more. The reason I'm writing it again because the area changes. This is the area plus a little bit more. And there is a force acting here. This force is equal to mass multiplied by the acceleration g, and the mass is equal to rho multiplied by a multiplied by bx2. Sum of forces in the vertical direction equal to 0. Sigma 2 multiplied by a negative. Let's make this is a positive. Plus the for the stress is equal to this. Multiplied by the area. Plus rho A dx2g is equal to 0. And you'll get this partial sigma 2 by partial x2 multiplied by area plus sigma 2 multiplied by partial A by partial x2 plus rho A g equal to 0. You'll get this differential equation. If you cancel terms and you do it by hand, you'll get this differential equation. This is the function of x, and this is the function of x2. My unknown is what is sigma 2. This is just, if you write it in a language of the differential equations that you're used to, this is like saying y prime multiplied by f of x plus y multiplied by f2 of x plus f3 of x equal to 0. That's the differential equation, and I'm looking for y. Now, I don't want you to solve something like this by hand, but you can use Mathematica to solve it. With the boundary conditions, we need only one boundary condition. Which is at x2 equal L, you're given the stress is equal to the force divided by the area at that point. After you find sigma 2, so I found sigma 2 at every point. So you're going to find sigma 2 as a function of x2. So now I'm going to go back to the problem. I have sigma 2 at every point. Knowing sigma 2 at every point, I can draw the contour plot of sigma 2. I can draw the contour plot of the von Mises stress, for example, because now I know the stress matrix at this point is made out of 0, 0, 0, 0, sigma 2, 0, 0. I have a function of the von Mises stress, calculate the von Mises stress, and find the von Mises stress at this point. So you can draw the contour plot and all the plots of all the variables that you want. And there are many examples in your book that you should look at. And if we have time at the end of today, I'll show you how to solve things like this and how to draw the plots using Mathematica. Problem 3 is similar, but the boundary condition here just is given as sigma on 1 is equal to 20 newtons per meter square, and the area does not change. So this will be easier and to solve by hand. So this is easier to solve by hand. Because the area is constant, the differential equation is easier to solve. And so, because if my object was like this, I wouldn't be able to solve it. I need a constitutive equation. And hence, chapter 5, the constitutive equation. And we're only talking about the neat elastic materials constitutive equations. I would like to replace these stresses that appear in the differential equations with these values. Why would I replace the stress with this? Because if you count the unknowns here, I've got U1, U2, and U3. If you count the unknowns here, they're 1, 2, 3, 4, 5, 6. If I'm able to replace 6 with 3, and I have 3 equations, then I'm able to solve my differential equation by the 3 differential equations of equilibrium. Now this is what I call the stress, and this is what I call the strain matrix. Again, this is a particular form of strain. There are many other forms of strain, but we're using this particular strain matrix for our equation, for the equations of small deformation, finite element analysis. And so this is what I call epsilon 1, epsilon 2, and so on. And the question is there a relationship between this and this? And for simplicity, now we know that this is a stress matrix, this is a matrix, and this is a matrix. But for simplicity, it has always been presented as a relationship between a vector and a vector. So basically, I take the matrix and grab the 6 unknowns and form a matrix of unknowns. It's a matrix, it's a vector representation of my stress. The stress is not a vector. The stress is a matrix, but just for the constitutive law, I'm presenting as, I'm taking a vector representation of it, because I'd like to relate those 6 unknowns with those 6 values of the strain. And not only this relationship, because it comes from the engineering, usually when it started, they were using gamma on 2 and gamma on 3, which are the engineering strains. And so the values that we use in the strain vector are 2 epsilon on 2, which is gamma on 2, gamma on 3, and gamma on 2. And now I need to form the relationship between this vector and this vector, knowing that, remember, the stress and the strain, they are not vectors. This is just to be able to present the relationship between them. And for linear elastic isotropic material, the relationship is given by the following. Epsilon 1 is equal to sigma 1 over E minus Poisson's ratio, sigma 2 over E minus Poisson's ratio, sigma 3 over E, 0, 0, 0. And you should be familiar with this relationship, with G is equal to E divided by 2, 1 plus Poisson's ratio. Don't forget, in this relationship, we're using gamma on 2 or 2 epsilon on 2. This matrix is inverted. Now, this is a 6 by 6 matrix. That is inverted. Now, why is this important for me? This tells me for any state of strain, I have a unique state of stress corresponding to that state of strain. And for every state, and so on. So there's a one-to-one correspondence between the stresses and the strains. You cannot have one state of stress that gives me 2 possible values of the strain. Now, whether this is physically, I don't know physically if this is the case or not, but mathematically, if I want to solve a certain equation and I'm replacing the stresses with the strains, I need to know, or I need this relationship to be one-to-one, because I'm usually looking for one solution. Or maybe there are other materials that have, for a certain state of stress, you might have different states of strain, but then you have to be looking for different solutions. Solutions corresponding to the possible states of strain. But for our numerical algorithm to succeed, or to work, it's better to have a one-to-one relationship between the stress and the strain, and this is the inverse of that relationship. Now, in your book, you should also look at this is just the relationship between stresses and the strain for isotropic linear elastic materials. There's also transversely isotropic. And there's also orthotropic materials. Especially if you're going to deal with such materials that have fibers or anything like that. Now, in many cases, we like, so this is a 6 by 6 matrix, 6 values of stresses and 6 values of strains, but we can further simplify the problems whenever we have symmetry. And we make the problem into a plane problem rather than a three-dimensional problem. Now, this is only valid in the following cases. So I have the assumption of plane stress, the assumption of plane strain, and the assumption of axis symmetry. These three assumptions allow me to reduce the unknowns, or reduce this 6 by 6, instead of having 6 by 1, 6 by 1, and 6 by 6, I make this into 3 by 1, 3 by 1, and 3 by 3. So it makes that relationship small. So what does plane mean? Well, it becomes a plane problem. So, but what does plane stress mean? Plane stress, as the name implies, the stresses are only applied in the plane. So at any point, the stress matrix has only these components. And the rest is 0. So what does it mean when the stress has only these components and the stress is 0? That means in the third direction, you're not applying anything to constrain your material from moving. So for example, usually plane stress is a state used for planes. You do not have any forces out of plane. You do not have any movement out of plane. You have a strain in the out of plane, but you do not have relative movement out of plane. The center line of that plate stays in the same plane. You do not have any shear stresses out of plane, and you do not have any forces out of plane, and the stress matrix at every point is given by this. And so this 3D can then be viewed as a 2D problem. So now this 3D, I can look at it as a 2D. With the only unknowns are sigma on 1, sigma on 2, sigma on 2, sigma 2. So let's look at the original relationship, and I'm going to say this is equal to 0, this is equal to 0, and this is equal to 0. Because sigma 1,3 and sigma 2,3 is 0, this will also have to be 0, and this will also have to be 0. Now, when sigma 3,3 is 0, what about epsilon 3,3? Is it 0 or not? In a plane strain, in a plane stress, I'm allowing the material to deform freely in the third direction, which means I have epsilon 1, epsilon 2, epsilon 2, epsilon 2, and I'm allowing the material to freely deform in the third direction. It can change its thickness, it can get thinner or thicker, depending on the stresses due to Poisson's ratio. So Poisson's ratio effect makes the material increase or decrease in thickness, and so I do have a value, or I might have a non-zero value for epsilon 3,3. If you manipulate those equations to get rid of epsilon 3,3 using the sigma 3,3 is 0, you end up with the following two equations. Equation that relates these with these, and a third equation that says, because I need to calculate epsilon 3,3, will be equal to this. the equations of finite element analysis, we're going to say, assuming plane strain, right away you know what I'm talking about. Or assuming plane stress, right away you know what I'm talking about. I'm talking about this relationship that you see in front of you. That the relationship between the stress and the strain is given by this. In plane strain is usually used for objects that are long enough and that are prevented from moving in the third direction. So for this assumption, this plane strain assumption, epsilon, or the strain matrix, is given by epsilon 1, epsilon 1, 2, epsilon 1, 2, epsilon 2, 2, and the rest are zeros. And because I'm saying that the material is restrained from moving in the third direction, what's stopping it from moving in the third direction is a value for the stress. And because of all those zeros, I can now look at my 3D problem. I can look at the 2D view of it. Assuming this force is all throughout, all along the object, and this force is all along the object. And usually, for these materials, you assume a unit thickness. You extract a sliver with a unit thickness. So, plane strain, this is 0, this is 0, this is 0. This is 0, this is 0. This is not necessarily 0. So you get the relationship between sigma 1, sigma 2, sigma 1, 2, and epsilon 1, epsilon 2, and epsilon 1, 2. Again, this is invertible, and you get another value for sigma 3, 3 that says sigma 3, 3 is equal to a number multiplied by u epsilon 1 plus epsilon 2. And so you're able to minimize the number of unknowns and solve the problem based on this assumption. Now, so this plane strain and plane stress is really useful in minimizing the number of unknowns in your finite element analysis. There's no need to model a whole 3D beam if you think of it as a plane, if it's possible to model it in a plane strain or in a plane stress condition. Now sometimes, for some materials, for some models, I've seen it where because the exact condition is unknown, sometimes people say, okay, well, I'm going to use the plane strain assumption as one extreme, and the plane stress assumption as another extreme, and try to see, okay, what are the extremes of my possibilities of my model. And so you might see that, okay, this is the plane strain assumption and this is the plane stress assumption. Now, in reality, or in practical, closer to the support, you do not have either. Or you might, for example, let's look at the plate. In reality, closer to the support, you are really constraining the material in the third direction. So this is not really closer to the support. It's not really a plane stress state. And also for this one, closer to the support, you have different behavior where this assumption of whatever assumption you're using of that cross section stays the same does not really apply. So you need to be aware of these things. Now the third plane assumption is axisymmetry. Whenever your object is cylindrical and the load is cylindrical, the geometry is cylindrical, the load is cylindrical, and the boundary conditions are cylindrical as well, then instead of looking at this in a 3D, I can extract a cross section and look at it in 2D, where this is the strain relationship. Now I make it into a 4x4 because in an axisymmetric problem, I have sigma on 1, sigma q2, and sigma on 2, and sigma 3,3, and epsilon 3,3. And epsilon 3,3, in this case, is related to the outward displacement, because epsilon 3,3 is equal to the circumference after deformation minus circumference before. Let's just write it at the bottom. So here's the relationship between the stress and the strain. Epsilon on 3 is equal to 0, epsilon 2 3 is 0, and this is 0, and this is 0. So I'm left with a 4x4, and I have an equation for epsilon 3,3 that's related to the outward displacement. This is the axis of symmetry. I don't really care for except the one cross section. It's moving out 1 by a distance u. When I look from the top, this moved out toward u. So now this is where it is, with a little bit of exaggeration. And this is r naught. This is r naught plus u. So the length epsilon 3,3 will be equal to the length after 2 pi r naught plus u. That's after deformation. This is before deformation. Delta over L. This is L, and you end up with u over r naught. So I'll give you 5 minutes, and then we'll cover chapter 6, the beam approximations, and this is, I think, the end of what we're going to cover today. And this is basically what you're also taking in 660. Yes?
Would you please give some real examples of plane stress and plane strain axis?
Real examples. Okay, what do you mean by real examples?
For example,
So plates in general are considered plane stress. If you have a plate, when you apply stresses on the plate, you're pulling a plate. Beams, when you take a beam, a thin beam, into and you model it, when you take it to the lab and you model it, usually you consider the beam as plane stress as long as you're not applying forces on the beam to the outside. Okay? Webs of, as long as you're not worried about the webs of beams, a web of an I-beam, as long as you're not considering buckling or out of plane movement of that web, this is a plane stress condition. Plane strain condition, consider dams, for example. If you have a dam, a really long dam, with load fluid acting on it in this direction, away from the support, this is a plane, I consider it a plane strain condition because I'm preventing the dam from expanding or contracting in the third direction. So any really long object that's constrained in the third direction is in a plane strain condition. A pipeline, for example. If you have a pipeline, a really long pipeline, it's an infinitely long pipeline. as long as you're not worried about the buckling of the pipe, you're just assuming that it's in plane strain because it's not going to contract or expand because of how infinitely long it is. As long as all the loads are the same. Because if I have a force here, I don't consider, like a force here, like something like that, for example. I can't consider this as plane strain because it's going to do something like that. Is that
How about axisymmetry?
axisymmetry. Examples of axisymmetry. So, see, when I did my PhD, I did axisymmetry, axisymmetric model, because I was looking at, well, I'm going to use the example. I was looking at joints where you have a bone on another bone with some cartilage here, and this was moved upwards and downwards. So this is a cylindrical object. So I didn't need to model the whole thing. All I had to do was model this part.